So to find the slope of this secant line, we just need to plug it into our blue boxed formula there. We're going to have 5 minus, and we can just make this 3, but 2 plus 1 squared minus 5 minus 2 squared. So that's 5 minus 9 minus 5 minus 4.
That's crazy getting all that over time.
Negative 4 over negative 1. We get that the slope of the secant line is negative 5. Questions at all? I just want to pull up the graph. Well, just draw the graph here of this function real quick. This is a parabola pointing down. It's been shifted up 5. And they're asking for the slope of the secant line at 2. If we kind of just look at 2, the slope of the secant line, it makes sense that we're getting a negative answer. So I just like to give you a kind of a visual representation that this answer, yeah, definitely makes sense for us. The slope of the curve y equals f of x at some point, x sub 0 comma f of x sub 0, is the number m, so it's our slope, as the limit as h approaches 0 of this f of x plus 0 plus h minus f of x sub 0 over h, provided the limit exists. This number is also called the derivative. So this is really exactly what we were doing in the last, previous sections. What, maybe like section number 2, that I think we've even had this exact diagram before. All right, so what's happening? We have our curve in red, and then we're looking at the slope of the secant line. I think I'm gonna put the curve in yellow so we can see it better. So there's our curve. Right now, this is our distance h in between our 2 points. And what's happening is if we take the limit as h approaches 0, that means that this distance h is going to get smaller and smaller. So it started here, and we had, a certain secant line. Well, now I'm going to make my h value smaller, and now h is only going to be this far, and we get a different secant line. Well, if we take the limit as h approaches 0, then we make h smaller and smaller and smaller until it's practically 0. So when it's practically 0, the 2 points are like on top of each other, and the secant line actually becomes a tangent line. And I need you, when I say tangent, to get out of trigonometry and get into geometry. That a secant line, by definition, is a line that hits a curve in 2 places. A tangent line hits another curve in exactly 1 place. So if we take this slope of a secant line, but make our h value get as small as absolutely possible, we turn this secant line into a tangent line, and since it's only hitting 1 point, it's actually giving us the slope of the curve at that exact point. It's like instantaneous slope. Do I have questions on that? I just realized in my mind that we didn't talk about that. I'm just having deja vu from making videos. Anybody? Questions? We're just making the h value smaller and smaller and smaller and smaller so that our secant line becomes a tangent line. And if it's a tangent line, it's only hitting the curve one time. Therefore, it's giving us the slope at that exact point, instantaneous. And that's really what calculus is. It's the instantaneous rate of change, not average. So, I'm sorry, questions? Anybody?
You like make sure they don't like come barking in here.
Jordan, are you talking to me or somebody in the background?
Oh, sorry. I didn't know my mic was on. I was talking to my girlfriend.
Okay. Asking her about the derivative?
Yeah.
Mm-hmm.
Yeah, Jordan.
What's up, G Money?
It's called a tangent line back to geometry because it's shooting off of the original graph, right?
So I know, and it's hard. Like I took this in 9th grade and then we never really did it again. So
Yeah.
a secant line, I remember when I did it in high school, it was always with like a circle and then a secant line hit in 2 places. Well, a tangent line, that line only hits in exactly 1 spot.
Okay, that makes sense.
Secant 2 spots. So that's why this, derivative thing is so powerful, because now we're not doing an average rate of change, we're doing an exact rate of change at that exact moment, an instantaneous rate of change.
That's pretty cool, honestly.
It really is. Anybody else? Questions? All right, well, let's let f of x be equal to 5 minus x squared, same function. Let's find the slope of the graph at x sub 0 equals 2. So this isn't going to be an average number, this is going to be an exact. This slope is going to be the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 all over h. We don't have a number to plug in for h, but we do have a number to plug in for x sub 0. And yes, you are going to be writing the limit as h approaches 0 so many times today that you're going to be like, this is ridiculous, but you're going to have to write it every single time. You won't want to have bad notation. You'll start confusing yourself. So this will be the limit as h approaches 0 of 5 minus 2 plus h quantity squared minus 5 minus 2 squared all over h. Those will be the limit is h approaches 0 of 5 minus. So hopefully you're learning that shortcut for squaring a binomial. Otherwise, write it twice and multiply it out. We are going to get minus the quantity 4 plus 4h plus h squared. And we've got 5 minus 4 here, so I'm just going to write minus 1 all over h. Distributing our negative. Combining like terms, all of our constants fall out. And we see this, right, with the difference quotient all the time. Every term that doesn't have an h cancels out so that we can cancel with the h in the denominator when we have a polynomial. So this is the limit as h approaches 0 of negative 4h minus h squared all over h. We factor out the h in the numerator. We cancel our factors of h. And we're left with the limit as h approaches 0 of -4 minus h. And at this point, it's safe for us to plug 0 in for h. That's why we had to do all this work, because way earlier, it wasn't safe to plug in. Now it is. So we can conclude that the slope of the graph at x sub 0 equals 2 is -4. Up here, we found the slope of the secant line starting at, going from like 2 to 3. And we got -5, but at the exact value of x sub 0 equals 2 is -4. And I feel like that makes sense that we're getting a slightly smaller negative number, because now I'm exactly at 2. And if we look at this diagram, the tangent line would be like right here. So it's still negative, but not quite as steep. So we're getting a slightly less negative number. Next, we want to find the equation of the tangent line at x equals 2. And we do this a ton in calculus, writing the equation of the tangent line. You can either use point slope form of a line or slope intercept form of a line, but we need to write the equation of the line having a slope of -4. And remember, to write the equation of a line, you have to have a point. They've given us x equals 2, but they have not given us the y value. So we'll take that 2 and plug it into our function f of x and get the corresponding y value. So we'll get 1. And we just have to write the equation of a line. Use the technique of your choice. I always prefer slope intercept form. Nope, point slope form. The slope of our tangent line at exactly x equals 2 is y equals -4x plus 9. Oh, I forgot. There we go. Questions, anybody? All right, well then I'm gonna let you guys do parts C and D. It's the exact same thing, except this time we're finding the slope and the equation of the tangent line at x sub 0 equals 2. I'll bring you guys out into rooms. Okay, so when we wanted to find the slope of the graph at x sub 0 equals 0, we start by finding the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. And this is just the difference quotient. I think what I'm going to show you shortly is more understandable, because we don't use the x sub 0. We just end up using the pure difference quotient, f of x plus h minus f of x all over h. So if you feel like a little shaky because of plugging in these numbers, don't worry, it's going to get better. But I did it that way to start with plug 0 in. So this first part that I have highlighted in yellow is where I've just plugged 0 plus h in for x, and then minus our original function evaluated at 0. And the cleanup on this one was pretty quick. Limit as h approaches 0, 5 minus h squared minus 5 all over h. Constants fall out. We cancel an h. Now it's safe to plug 0 in for h when we have the limit as h approaches 0 of -h we get that the slope of the graph at x sub 0 equals 0 to be 0. Well, so questions on that? Oh, we see that slope of 0. That tells us we have a horizontal line. We know that right off the bat. We want to write the equation of the tangent line as at x equals 0. So we need our point and our slope. And we end up with the equation y equals 5. I want to go back to the graph of this function. Notice that what we're doing is finding the equation of the tangent line at x equals 0. And notice that we end up with a horizontal line, and look where it's at. It's at that vertex. So even though we're not going to cover this in here, it's for calculus. I can't wait, especially because I've had so many of you for college algebra. I can't just let them have all the thunder in the world. All right. Remember when we were graphing polynomial functions, right? And we just kind of had to BS the graph a little bit. We're like, how high? I don't know, this high, right? And we drew in the graph. Well, the way that we're going to use calculus to figure out how high to make those peaks is that's where the slope of our tangent lines, aka our derivatives, are equal to 0. So that's what you're going to do in calc. They actually call it the first derivative test that you use for graphing, and you find the derivative, then you set it equal to 0, solve for x, and that'll tell you at what x values you have these horizontal tangent line. So that tells you where like your peaks and valleys have to be on your graph. It's awesome. Questions on our part D?
That's the, well, it's not the part D, it's about the problem. H always is gonna approach 0, or it depends on the problem?
No, always. Because if H doesn't approach 0 and get smaller and smaller and smaller, our secant line doesn't turn into a tangent line.
Okay.
So H is always getting as small as theoretically possible so that the secant line turns into a tangent line.
Okay, thank you.
Anybody else? All right, let's try another one. Ooh, this time a rational function. We know it's going to be great. What we're doing this time, though, is finding the slope of the tangent line at x equals 0. Now, you'll notice that the notation's already the same changed. It could be x sub 0 equals 0, or they could just say x equals 0. Which I know makes it confusing, but at the same time, don't get so caught up in the notation. X sub 0, whatever. You know, it's just a variable used to represent an unknown x value. Sometimes it's x1. To find this slope, we're going to be looking for the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. And I don't know, maybe I should have had the step before that we're finding the limit as h approaches 0 of f of x plus h minus f of x all over h. Again, this is the same as the one we had before where we had the subscripts of 0. It's just they didn't write the subscripts of 0 this time. F of 0 plus h, well, that's going to be 0 plus h minus 1 over 0 plus h plus 1. Then minus our original function evaluated at 0 all over h. And then we start cleaning it up. This is h minus 1 over h plus 1. So we're going to have minus a negative 1, so that becomes plus 1 all over h. What should we do next? Because it's easy to get caught up in the algebra or forget what the algebra move is.
Would you simplify the numerator?
How do you want to accomplish that? Like, what do you mean by that?
Like actually like solve like multiply the 1 by the h plus 1. I don't know.
Okay, no, you have good ideas, Aaron. You have good ideas. So there's two options. We can, with a rational expression like this, well, hold on one second. I need to see. Sorry. With this complex fraction, we have two different options. We can either add the numerator together so that we end up with one fraction over one fraction and then multiply by the reciprocal of the second fraction. Totally great. A more direct route, though, to simplify is to multiply each individual term in the complex fraction by the LCD of all the fractions. So if we multiply absolutely everything by h plus 1, make sure top and bottom, then all of the denominators, individual denominators cancel out, and we're left with just a rational expression and not a complex fraction. So Aaron, I think you were describing the first way, not wrong at all. It's just a longer process. And we really, going into calculus, I don't want to say we want to use all the shortcuts because we do need to understand what we're doing, but we can't spend tons of time on the algebra when we're having to work through the calculus. So I would encourage the more direct route. Combining our like terms in the numerator, all our constant terms fall out. That's 2 over h. Or I'm sorry, 2 times h over h times h plus 1. H's will cancel out. We get the limit as h approaches 0 of 2 over h plus 1. And now it's safe for us to plug 0 in for h. We end up with the slope of our tangent line being equal to 2. And you keep writing the limit as h approaches 0 until you actually plug 0 in for h. Questions at all? For a function f of x, the derivative at some point x, we've defined the derivative to be the slope of the tangent line, and we've defined the slope of the tangent line to be the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 all over h. So we conclude that the derivative is the limit as h approaches 0 of f of x plus f of x sub 0 plus h minus f of x sub 0 all over. It's so unnatural for me to say that sub 0 in there. Makes me fumble over my words. There are a ton of different notations that mean derivative. So this is an interesting story here. Let me share with you some history of calculus for you. In the 1600s, both Newton, right, that's when Newton was doing all his amazing discoveries, and Newton was in England, and then there's another mathematician named Leibniz, and he was in Germany. And at the same time, independent from each other, they were discovering calculus. They were coming up with it. Well, Newton frequently waited to make any kind of publications. So Leibniz actually published first, but Newton had been working on the math behind calculus first. So basically, these two men discovered calculus at about the same time, published at the same time, independent from each other. So since they were each doing their own mathematical work, they each came up with their own notation. So we have two pretty different notations. Newton's notations use this little, I don't know, well, we call it a prime, this little tick mark right here. So we would say f prime of x or y prime. And that just means the derivative, that tick mark notation. Then Leibniz, he was using this other notation over here. So df dx, this means the derivative of f with respect to x. And since y and f of x are typically interchangeable, we also see dy dx, the derivative of y with respect to x. Then, well, sometimes, and this is still Leibniz notation going over here, sometimes they put the f of x off to the side. So you'll see d dx and then the f of x off to the side. These are what you're going to see in Calc 1. These are some other more obscure notations that you might see in like Calc 3. But yeah, two different notations. I'm going to use them interchangeably because really they get used interchangeably in the math world, and I need you to be comfortable with both of them. Once you get into more advanced calculus and differential equations, you'll see that we use the Leibniz notation more frequently. I usually use Newton's notation just because it's less to write. But yeah, it was like, you know, this battle of these mathematicians for years on who discovered calculus and all this stuff. It isn't calculus. They weren't doing calculus as we know it today, but they were doing the beginnings of the work that opened the door to the calculus that we have today. All right, that's why there's two different notations. If our first derivative, f prime of x, exists at a particular x, we say f of x is differentiable at that x. And differentiable just means that it has a derivative, because sometimes the derivative doesn't exist. If f prime of x exists at every point in the domain of f, we call the function f of x itself differentiable. So like polynomials that are nice, smooth, continuous function, the derivative exists at every point. It's defined everywhere. It's nice. So that whole function is going to be differentiable. Trigonometric functions, rational functions, radical functions, they all fall into this category where their derivative exists at every point in the domain. So here we go. Same definition. I'm just taking out the sub-zero. And this is how I think of derivative. If a function f of x is differentiable at every point in an interval, the derivative is a function itself. That function, f prime of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. I think this is the much easier way to do problems than I introduced it, where we were actually plugging the 0 in. Frequently, we're not just trying to find the derivative at one particular point. That's not usually the end of the question. There's usually a lot more to do. So I think it's easier to find the derivative for the whole function first. And then we have that equation that we can evaluate different places and answer different questions. So let's find the derivative of each function. Just to mix it up, I guess I'll use Leibniz this time, dy dx. This is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And they don't have to give it to us in function notation to use, the function notation in our difference quotient. Because, I mean, how else are you going to write it? You can't write y of x plus h. So this is the limit as h approaches 0 of 1 over 3 times x plus h minus 1 over 3x all over h. Certainly not safe to plug in until we get rid of that factor of h in the denominator. So it's time to start simplifying. This is very similar to the last one we did because it's rational. So every time we have a rational, we multiply each one of the terms by the LCD of all the individual terms. What's our LCD going to be this time?
Three x plus 3h.
You're super close. What you did was you just distributed this right here, right? Now don't forget to look at this denominator. That denominator over there is 3 times x.
Would that be both of those denominators multiplied together?
So we could just do 3 times x plus h times 3x, but that's not going to be the LCD. Because they both have a 3, we don't need to make it 9.
Right, okay.
Our LCD is going to be 3x times x plus h. Everybody okay with that LCD? All right, well, let's simplify. So here the 3 cancels and the x plus h cancels, and I'm left with only an x here. I'm going to hit it with a highlighter so I don't forget about it. And then here the 3's and the x's cancel. I'm left with minus 1 times x plus h. And then nothing cancels in the denominator. I just have all that together. So that'll be the limit as h approaches 0. X minus 1, x plus h, all over 3xh times x plus h. Continuing to simplify, we will distribute in our numerator. And still writing, the limit as h approaches 0 every single time. Combining like terms in the numerator. So negative h over 3xh times x plus h. Now we can cancel that factor of h in the denominator, leaving us the limit as h approaches 0 of negative 1 over 3x times x plus h. Although I still have an h in the denominator, it is safe to plug it in. That's going to be negative 1 over 3x times x plus 0. We get our derivative to be negative 1 3x over 3x squared. And now that we have this derivative function, if they want to say, hey, what's the slope of the tangent line at x equals negative 5, I just plug negative 5 in for x. If they say, what's the slope of the tangent line at 6, I just take 6 and I plug it in for x. So I like having the function and then evaluate at a particular number. So know that that is an option. Now, I can't speak for your Calc 1 instructor if they're going to make you do it like this. But like this one, I don't know. I hate that x sub 0 notation. And I feel like it's more confusing when I have 2 plus h than if I just had x plus h. Because I'm so used to the difference quotient. So I would find it the way we just did it and then plug in x equals 2. Questions, anybody, before we do the next one?
So that would be dy over dx equals negative. Okay. Okay.
Got it. Yeah, sorry. Or we could write y prime, or we could write f prime of x, any of those notations. This is our derivative function.
Yeah. Okay.
I think I'm going to switch to the prime notation pretty quick. I like the prime notation for basic calculus. I like the dy dx for more advanced calculus. I already got to write the limit so many damn times. Let me at least get the shortcut on the derivative notation. And I also like this, the f prime of x probably the best, just because it's like, oh yes, this is a function. And then if I want to find what's the derivative at 6, I have function notation that I can use that helps me remember what I'm doing. So I think f prime of x is probably my first choice. All right, to find f prime of x, we're going to take the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x all over h. This is the limit as h approaches 0 of the square root of x plus h minus 1 minus the square root of x minus 1 all over h. So who remembers how we simplify our difference quotient when it's a radical?
Everything.
Do
Say that
square
again.
both?
Anna,
Can
what
you
did you say? And then I'll come to you, Jordan.
Sorry.
Yeah, I said square root too.
You said square both of them as well?
Yeah.
Okay, Jordan. So what, you mean like square the top, square the bottom?
Yeah.
That is not a legal math move.
Oh,
Okay, that'd be like saying, all right, I got the fraction 1/2, and now I'm just going to square the top and square the bottom, and I'm going to tell you that that's equal to 1/4. Right, 1/2 and 1/4 definitely have different values, so that is not a legal math move to square top and bottom.
What's that? Is it that conjugate multiply?
There we go. The way that we get rid of the radical, right, for it to be a legal math move, we need to multiply the top and the bottom by the same thing. We can't square the top and the bottom, but we can multiply the top and bottom by the same thing, because then this is just a fancy form of 1, and multiplying by 1 doesn't change the value. We are going to multiply top and bottom by the conjugate of the top. And of course, it's going to be the conjugate of the top because I don't have a radical in the bottom. This is what will eliminate our radicals, so we can gain access to this h in the numerator and ultimately cancel it with h in the denominator. So this is going to be the limit as h approaches 0. With conjugates, all we have to do is multiply the first two together and the last two together. Square root of x plus h minus 1 times the square root of x plus h minus 1 gives us x plus h minus 1. Now the next one, this is where, it's easy to make a mistake. We have a negative times a positive, so it's going to be minus, but we have to put the next part in parentheses. Square root of x minus 1 times square root of x minus 1 is x minus 1. And in the denominator, we do not want to distribute because we want to cancel that factor of h. And if I distribute, well, then I won't have a factor of h anymore. Distribute in the numerator. And combining like terms. Oh, that's just h down on the top. H's cancel out. And we're left with the limit as h approaches 0 of 1 over the square root of x plus h minus 1 plus the square root of x minus 1. And although there's still an h in the denominator, it's not a factor of h, so it's safe for us to plug in. We're going to get 1 over the square root of x plus 0 minus 1 plus the square root of x minus 1. Well, that's going to be 1 over the square root of x minus 1 plus the square root of x minus 1. We're going to say f prime of x is equal to 1 over 2 times the square root of x minus 1. Questions? I don't know that any of this is particularly difficult, but it's easy to get caught up in the algebra. I've said how many times, well, calc's not hard, it's the algebra within the calc that's hard. So remembering what the trick is about multiplying by the conjugate, doing it correctly, not dropping a sign off the face of the earth, I really feel like that's where it's challenging. So you got to just take your time. And it wouldn't be a bad idea to start creating a list of, I don't want to say tricks or techniques, algebra techniques that you need to use. Oh, when it's this, I multiply by the conjugate. Oh, when it's a complex fraction, when I started with a rational function, I'm going to multiply each one by the LCD. I would have to start a list for yourself. But also then, just to preview, so you're not thinking, oh my God, am I really doing all of this for all of next semester? No, we learn tricks. So if I were finding this derivative, it would go this fast. And you're going to learn these same tricks. So, right, negative exponent takes us to the bottom of a fraction. 1/2 times 1 is 1/2. So I'm going to put the 2 on the bottom. And that's exactly what we got. So you're going to learn tricks, but you're going to do it by definition in the beginning. And in fact, your teacher is going to let you leave it like this and not even rewrite it with the thing in the denominator, probably. All right, I'm going to break you guys up into groups to do the next one. The next one's a polynomial, so it's the nicest one. Down to 8. All right, so everybody sounded pretty good that I talked to, that we just plugged in to our difference quotient. It cleaned up nicely. We end up with f prime of x equal to 2x minus 6. Anybody, any questions? Well, I still have, I don't know, at least a half an hour worth of stuff in this section, so I'm just going to call it a day. So that means that our test will not be on Wednesday. We're gonna have to make it like Friday next week because I'll finish this stuff up on Monday and then we can have our test. Maybe I'll make it like Friday over the weekend to give you guys some time to practice. I would encourage you to kind of look ahead. I got all the videos posted to look ahead so that you feel extra good about it, or even rewatch. You could rewatch this video, but this is way longer than like the more direct lecture that I have in those short videos that, to get real comfortable with this. I'd encourage you to practice a bunch. This is really where you want to do a large volume of problems so that you remember all of those techniques about, what do I do when it's rational? What do I do when it's a radical? What do I do when it's this? So I would encourage you to do a bunch. I know it's a pain in the ass to write the limit over and over again, but you gotta do it. Anybody, any questions?
Is there a section in the book that we could get practice problems from?
Sure, this is section 11.4 in the textbook. You're talking about the real textbook, right?
Yeah.
Yeah, so you can pull that off of My Math Lab. You can get in the study plan and pull questions off of 11.4. Now, of course, unfortunately they just want you to type in the answer. So if you find that you're getting ones wrong, send me pictures of your work so I can look through your algebra. That's really what I need with these types of problems to be able to help you.
Great. Thank
So,
you.
I do plan on hanging ceiling joists all weekend, but evening time, I will be like 9 o'clock, tired. I will be happy to jump on for video chats with any of that if you guys have questions. So, all right, everyone have a wonderful day. I will be sticking on for office hours if you need anything.
Great. Thank you.
Good weekend.